Welcome to Connected World, a podcast for engineers to learn more about the trending topics influencing the connected world and technology turning today's impossible into tomorrow's awesome. Hello and welcome to Connected World, a podcast from TE Connectivity. I'm Tyler Kern. Thank you so much for joining me for this episode of the podcast. Today I'm speaking to Christian Koehler. He is the Manager of Product Management for RF Solutions at TE Connectivity, and we're going to be discussing wireless IoT challenges in the super connected world. So Christian, thank you so much for joining me.
Hey, thank you so much. Thank you for the kind invitation. Very much appreciate.
Well, I'm really excited to get your expert analysis and insights on this topic today, Christian. And just to begin, this is a question that we've asked several of our experts on the podcast so far, but what are some of the biggest challenges facing wireless IoT in the connected world right now?
This is really a big thing. I would start with a few global challenges. I would call them global challenges, like technical challenges, which belong to coverage. So IoT, wireless IoT, devices, they need to cover a certain area. Energy efficiency, for example. The data rates, which are required those days. Other technical features in combination with wireless. So those are the technical challenges. Then there were some commercial challenges, which is like quality of service. Take quality of service for ultra reliable, low latency communication. You might have heard about this. And so this requires very short latency, very quick reaction of wireless services. And so the quality of service is becoming much more important in those days for certain applications. Then it's security. Think about all the devices which are connected. They have to stay secure and they should not be hacked at any time. And they should be upgraded for security reasons and so on. Last but not least, cost. And scalability are two important parameters in terms of commercial challenges. And the third thing is the ecosystem. So when thinking about the ecosystem, is the solution which is going to be developed future-proof? Is there a global rich interoperability given on devices when the market should expand from the local market to other regions, for example. So there was enhanced mobile broadband, which is a challenge data rates going up to 10 gigabit per second and more. There was massive machine type communication. Massive means like a million or a couple of million devices in a square kilometer. There was the ultra reliable, low latency communication. And there are a few wireless standards which which developers can select from. There was short range, there was low power, wide area standard, and there was a traditional cellular standard available. And depending on the area to cover, on the energy consumption requirements and the data rate requirements, the one or the other standard might be the good one, the right one for this specific application. Now, what we also face is a very strong exponential growth of wireless traffic. That means the channels, they get more and more congested. So there are not so many new frequency bands going to be added to the spectrum, at least in the sub 6 gigahertz spectrum. Just a few new frequencies are available. There will be lots of interference. So with exponential growth of traffic, there will be interference everywhere, which is kind of a competition in air for the best connectivity. There was also complexity of antenna design. So what do I mean? Antennas are different from regular passive components or from most of the regular passive components. Antennas, they need to be taken differently. There was a tendency to avoid this complexity or even ignore this complexity. There was a tendency to take antennas as any other passive components like capacitor or resistor or so. The next challenge is the understanding of RF requirements. So how do I know my antenna is good enough? And how do I know it's good enough today? And even more important, it's good enough tomorrow when the exponential growth further continues, more interference is being added to the channels and so on. There was a high level of integration of functionality into IoT devices, which is another challenge. So lots of key performance indicators have to compete. So the one want to have the biggest battery, the other one want to have the biggest display. We want to have the biggest antenna. And there was a constant fight for the best possible compromise within those devices. There was also power consumption. I think I mentioned that already. Cost performance ratio. Another big challenge, what we are facing is experience in the market. So experience of startup companies, for example, even well-established companies who did not deal with wireless services in the past, when all of a sudden there need to be wireless connectivity integrated to devices, and the level of complexity is taken very often to, I would say, a little bit too loose or too easy, which can lead into problems.
Absolutely, absolutely. So there are obviously a lot of challenges in the market right now, and a lot of challenges for engineers in the industry. And you mentioned several there. Frequency congestion and added complexities and things along those lines. So, Christian, how are you seeing engineers face these challenges, and what innovations are coming out of these challenges to help solve these problems for the future? If we look into the industry, I think the most advanced engineering groups can be found in the area of smartphones, of handhelds, so wireless handhelds like tablets or even laptops. So developing antennas for those devices, there's nothing left to coincidence. Anyone in the loop, based on decades of experience, knows what is important, what need to be considered. So a few people, they really know how to design antennas. Nothing goes wrong. They get to a super good working compromise very quickly. But often customers have to implement wireless services. They haven't done this before. And just the availability of hundreds and thousands of so-called standard antennas in the market make believe that what is written on the data sheet is kind of true. And what I can say from experience, everything is true except RF data. So because antennas and antenna implementation cannot just rely on RF data based on the data sheet. As for any other passive components like capacitors, what's written on the data sheet is true. For antennas, it's also true, but it's related to, let's say, a reference ground plane measured in free space and so on. So it's very dangerous to use data sheets, but very often this approach is taken. So select an antenna from the catalog, put them on the board, switch on the board, and it's not working. And then sometimes trouble arrives how to solve this problem afterwards. So antennas, usually, we get a lot of requests from IoT opportunities where antennas need to be small and cheap. We need to have the smallest antenna, the cheapest antenna. And I'm asking myself, what is small? So what is cheap? And coming back to the phone guys, to the mobile phone guys, they try to make antennas as big as possible. And so cost is also super important. But what is the purpose of a cheap antenna when the connectivity is not good enough? But we also see antennas get implemented very late in the design cycle of new devices. They get squeezed somewhere in between other components of existing devices, which need to be upgraded by wireless service. And so the understanding of the device as part of the antenna is very often not so well developed. And TE can support to tackle those challenges by a holistic approach based on decades of experience with mobile phones, which to me, I would call them now as challenging devices. They are small. They have to fulfill strong cosmetic requirements. They have to be battery efficient. They have a big battery, a big display, and so on. So everything is contradictory to the function of antennas, and still up to 6 or 7 or 8 antennas have to work in such small form factors. So this is where TE team can really support. But we see the approach is very often not tuned and tailored to
the specifics of antennas.
So, Christian, one of the things that you mentioned was when in the design cycle, antenna implementation was considered, that normally it's coming too late in the process, they're being squeezed between other components. From your perspective, what is a good time during the design cycle to consider where the antenna should go and the implementation of the antennas within the device?
Well, this is a very good question, and there are a few clear statements from guys like AT&T. I would say there are three key elements for a design cycle or for a new development of a device. First is the definition of a use case, a clear understanding of RF requirements. For example, an HD security camera that requires a omnidirectional pattern. It requires a strong signal, so good connectivity, maybe 2 or 3 antennas to run MIMO for a good throughput. Whilst an energy monitor, which has to transmit a few bytes or kilobytes per day and is battery driven, has totally different requirements, and still the antenna need to be very, very efficient. So the second key element to me is preparing a link budget to understand worst case conditions in the field. Even if the device is working in the lab, that doesn't mandatory mean it's working very well in the field, in rural areas where the signal is fading. And the question is, do we have enough margin to guarantee required performance? And the third key element is the consideration and understanding of device conditions. What size of device do I want to make? What components? What other antennas? What shielding cans? What batteries? What other your transformers or so would have to be in close proximity to antennas, which can have an impact. So those three elements should describe the level of complexity which is involved in antenna design. And this is making clear antenna cannot be designed at the end of a design cycle, right? Mm-hmm. Be considered right at the beginning of a product, or even furthermore, even if we think about antenna design right at the beginning of a product cycle, any mechanical change of a device must be verified related to a potential influence to the antenna performance, which requires rapid tuning, adjustments on time when required. I would like to talk about an example from a power meter. We came in early, and there was a requirement to get an LTE antenna and a power meter for remote control, for remote monitoring. And everything was perfect. So the PC board was perfect, the ground plane was perfect, the antenna was located in a perfect place. And during the design, a supercap had to move a few millimeters towards the antenna, which was killing the low-band performance completely. So it took us a while to find out the root cause. But such minor changes in the design of a device can have a very, very significant impact. So again, I'm pretty sure we should talk as early as possible in the design cycle about antenna implementation.
You know, Christian, we've talked a little bit about how antenna performance is affected by its placement, and you had a great example there of just an example where the antenna's low band performance was degraded based on components that were placed nearby it and things along those lines. So tell me a little bit more about performance indicators for embedded antennas. How is antenna performance measured, and what does that look like?
If you think about a successful design of an integrated or embedded antenna, I would not like to talk so much about external antennas because they are rather easy to implement, and measurements and performance indicators are rather predictable and repeatable, not so on embedded antennas. So for design of embedded antennas into wireless device, a number of measurements must be made to quantify the antenna performance in the actual product. So there's no use to measure the antenna in free space and then implement into the device and leave performing similar. So there were a few performance indicators like bandwidth. So bandwidth is very important, which has to do with antenna design, with antenna location. Another indicator is gain, of course. And finally, some people, or even a lot of people, they look for high gain, except for antennas which are supposed to be directive for point-to-point connections or so. The antenna should rather be little, like 0 or 2 dBi. So very little gain means very, very good omnidirectional performance. And a lot of IoT devices, they have to perform in a random environment. So nobody can predict upfront, where's my gateway, where's my access point with relation to the IoT device. So it can be in front, it can be on the back side, it can be to the right, to the left. So whether the IoT device performs with an omnidirectional perfect. If there was bandwidth and gain under control and isolation, I should not forget isolation. In some of the devices, there are multiple antennas needed. They should not influence each other or interfere into each other. The very, very important simple thing is efficiency. So let's measure if the efficiency and the single most important parameter to be measured. Sorry, the efficiency of my voice just dropped a little bit. And you might have seen or heard what happens. So even if my bandwidth is fully okay, my gain is okay, the isolation is okay, but if the efficiency is not good, it's very hard to understand. So even if there was a lot of interference, right? So if there was interference and the antenna need to compete with the interference and get through and speak loud enough. So efficiency, we have seen efficiency to be the single most important parameter to be measured, in particular for embedded antennas, which can have kind of degraded efficiency due to whatever happens, tight integration, other potentially impacting components in close proximity. So the antenna need to act as a transducer between the radio and propagation medium. And if there was an impact to the antenna, it won't speak. I want to explain this on a worst case scenario. We had a customer that had the antenna perfectly tuned. The bandwidth was super good, isolation, so antennas did not interfere with each other. And it was an antenna for a printer. So finally, on the outside of the printer, there was a paint with metal content. So with painting the printer housing with metal containing a varnish, actually the customer created kind of a Faraday cage. All parameters were perfect on the antenna, everything nicely tuned, but the efficiency was 0, and the printer did not work as expected. And all the other parameters became of minor importance at this time, with a very simple single impact of a Faraday cage.
That's really interesting, and I appreciate the object lesson, the example of what it sounds like when certain aspects aren't working, either interference or with your voice being muffled and hard to hear. I thought that was a really great way to describe it, especially on a podcast, which is a listening medium anyway. So I thought that was really good. So one of the things you talked a lot about efficiency. What is the difference between VSWR and efficiency?
I'm glad you asked this question because VSWR, called VSWR, standing wave ratio, is kind of a measure of the impedance matching of loads to a characteristic impedance of a transmission line or so. So in other words, the radio module, the RF module, has an impedance of 50 ohm. And within the frequency, the antenna should also perform with a 50 ohm impedance. Then the VSWR, the voltage standing wave ratio, would be close to 1, which is the ideal case. If there would be a shortcut instead of an antenna, the VSWR would be infinite. That would be the worst case on the other side. It's to tune the antenna, it's enough to have a network analyzer. So you can see how well the antenna is tuned. It does tell much about the antenna performance. It's telling it's good matched. Together with a bandwidth measurement, you have got a very good basis set of information for the antenna characteristic. However, within a device with all the chassis closed and all the components inside, and ideally even switched on to have other sources of noise like interfaces interfering with the antenna, then the efficiency measurement is a totally different thing. Antenna efficiency is based on comparing the total radiation power to the input power to the antenna terminals. In easy words, if an antenna has an efficiency of 10%, then 90% of the RF power, which is transmitted from the RF module, is converted into heat or something else, but not radiated into air. So 10% radiated, 90% transformed into heat. We don't want to make an oven, right? We want to make an antenna. So now the question is how to make this better. How to find out what is my efficiency? It's required to have an anechoic chamber, or better, a SETI-mode chamber, which is an anechoic chamber with a ring of sensors. There was a turntable needed to measure the three-dimensional radiation pattern. That takes some time, and then it's kind of an integration of the power by the radiation, the three-dimensional radiation pattern that is providing the efficiency. When this equipment is not existing, a network analyzer is good to check the basics of an antenna, but it's not telling anything about what is my efficiency. So how good is the transmission and the reception of the end device? So for those kind of parameters, there was an anechoic chamber needed. And both values, VSWR and efficiency, by the way, they need to be measured with an antenna fully installed in the device, with all components installed, and so on. What happens if the efficiency is zero? You can imagine there was no wireless connectivity, customer not satisfied. And if the efficiency is good enough for the lab and not good enough for the worst case scenario, the same may happen, unsatisfied customer. So therefore, efficiency measurement is giving a good indication of what wireless performance I can expect in the field.
Excellent. Well, Christian, we're coming to the end of our conversation here today, but I want to give you the opportunity to close with anything that we may not have discussed so far about antennas and IoT that maybe you wanted to mention before we finished up, or even just a summary statement just on the state of the industry. So if there's anything we haven't discussed yet, or you want to kind of give a closing statement, feel free. Let me turn it over to you.
One issue that's coming up frequently is narrowband, the famous narrowband IoT, a service that's providing safe service and registered service and licensed bands with some kind of liability. So sometimes there was kind of a misunderstanding. Narrowband, I need narrowband antenna. That narrowband IoT actually works within the regular LTE bands. And even if the service itself, narrowband, is running with kind of a 200 kilohertz bandwidth, that does not mean it's a narrowband antenna. So the antenna for narrowband IoT is basically an LTE antenna. An LTE antenna implementation requires wideband antennas like 617 megahertz to 2.2 or 2.7 gigahertz, so very wideband. It requires a lot of experience, a lot of competence to get them integrated very well. And this is just one point I would like to mention. So narrowband IoT sounds easy, maybe is easy, but the antenna implementation requires a much more carefully approach compared to single band antennas or wireless services like LoRa, which is 868.915 megahertz, or Zigbee or Bluetooth, 2.4 gigahertz or Wi-Fi or so. So this is all relatively easy compared to implementing a narrowband IoT cellular antenna. As a closing, I would say the antenna is a very important connector. We are a connector company, right? And for me, antenna is the most important connector of wireless devices. It's a critical component, and it's good to have partners with not just the equipment available, but also the competence to integrate antennas and tune them. And basically, the successful integration of an embedded antenna into wireless devices depends on the understanding that the entire part of the device is part of the antenna. Very likely this is the case. So the antenna cannot be added at the end of a design cycle. It must be designed from the very beginning. And what we sometimes realize, fixing antenna problems in a certification lab is time-consuming, it's very expensive. And so this is where TE Connectivity is well known for its professional approach to generate high-performance embedded and external antenna solutions. I would call an antenna most likely antenna solution rather than just a component. And this is addressing the needs of the exponentially growing wireless traffic. And TE engineers have been developing antenna solutions for some of the most challenging applications during the last 20 years, I would say, and we would be very happy to partner with our customers and make a antenna development very easy and simple, even if it is super complex, happy wireless.
Excellent. Well, Christian Koehler, Manager of Product Management for RF Solutions at TE Connectivity. Christian, thank you so much for joining me today and diving into the challenges in the super connected world for wireless IoT and talking about antennas and so much more. Christian, we really appreciate your time today.
It has been a great pleasure, Tyler. Thank you very much.
Well, thank you. Thank you very much. And thank you to all of our listeners out there for joining us for this episode of the show. We appreciate it very much. Of course, we have previous episodes you can go back and listen to, as well as future episodes. So make sure you're subscribed there on Apple Podcasts or Spotify. And we'll be back soon with those new episodes. But until then, I've been your host today, Tyler Kern. Thanks for listening.